Hi students, greetings to all and of course this is my 19th video for the first unit of engineering thermodynamics and deals about basics and fundamental concepts of thermodynamics. And of course I have imported all the topics in the first unit in various videos covering from first fundamentals to applications of first law of thermodynamics and reducing the SFE equation for various devices. And the problems in the last videos were discussed. Hope that you have all watched the videos and of course worked out the various examples and the problems which was solved and the derivations have been tried by you. And now I am going to launch two more videos for the recap corner for first unit, and this is my recap video number one for first unit of thermodynamics. Okay, shall we move? Okay, so this is the first part of first unit, that is half of the part is being covered in this video. On other topics will be covered in the next video. Now regarding the basic concepts, thermodynamics deals with the relationship among heat, work and the system properties which are in equilibrium, right? Then thermodynamics can be studied by adopting either a macroscopic or microscopic approach. System represents a finite quantity of matter or a prescribed region of space wherever concentration is being given, and it might be of three types: open, closed and isolated system. The envelope surrounding the system is called boundary, and the boundary may change its shape and size. Everything external to the system is called surroundings or environment, and a system together with the environment forms a isolated system. Like universe is our best example for isolated system. Properties defines the condition or the state of a system. Intensive properties do not depend upon the mass of the system, whereas extensive property purely depends upon the mass of the system. All the specific properties are coming under intensive properties. When a path is completely specified, then the change of state is called a process. A process represents a transformation of the system from one fixed state to another form of state. A reversible process is one which can be stopped at any stage and reversed so that the system and the surroundings are exactly restored to their initial states. Infinite slowness is a characteristic feature of a quasi-static system or a process. A reversible process is a quasi-static process, but a quasi-static process need not to be a reversible process. Any process or series of processes whose end states are identical, they are called as a cycle or a cyclic process. A system is said to be in thermodynamic equilibrium if it simultaneously satisfies the condition of mechanical, thermal and chemical equilibrium. Phase refers to the quantity of matter which is homogeneous throughout in chemical and physical structure. A homogeneous system is of single phase, whereas a heterogeneous system consists of two or more phases. The types of matter normally considered in engineering thermodynamics are gas, vapors, liquids or any non-reactive mixtures of these. Okay, so and then now if we move to the various property, especially temperature, it is a very important property because the heat is measured in terms of temperature. Degree of heatness or coolness of the heat is being measured by the temperature. Okay, so the temperature of a system is that the property which determines the ability of the system to transfer energy in one form of heat to other state of the system in thermal contact. two systems would be equal if temperature if no change occurs in any property when they are brought into the communication. When they are brought into communication, there should not be any temperature or heat exchange occurs, means then they are said to be in equal in temperature. Two systems which are in thermal equilibrium with a third system, and they are in all the three will be in thermal equilibrium with each other, and this is the essence of zeroth law of thermodynamics. And zeroth law, like other law, is based on experience and does not have any mathematical proof. The zeroth law provides the basis for temperature measurement. Temperature scales are defined by assigning numbers to the ice point, to the steam point, and to the equal spaced marks between them. The ice point is the equilibrium temperature of ice with water at standard atmospheric pressure, and it is assigned a value of 0 degree Celsius in the Celsius scale and 32 degree Fahrenheit in the Fahrenheit scale. The steam point is the equilibrium temperature of pure water with its own vapor at atmospheric pressure, and it is assigned a value of 100 degrees Celsius on the Celsius scale and 212 degree Fahrenheit on Fahrenheit scale. Between the steam and the ice point, there are 100 equal parts of Celsius scale and 180 equal parts in Fahrenheit scale. And thus, the correlation between the temperatures measured on the Celsius and the Fahrenheit scales, or which how it could be converted from one form to another form by using the relationship of TC, that is stands for temperature in Celsius scale divided by 100 is equal to TF, that is temperature in Fahrenheit scale minus 32 divided by 180. The Kelvin temperature scale has been defined with the reference point to a single point called triple point of water, which is assigned with a value of 0.01 degree Celsius. At the triple point of water, the ice, liquid water and the water vapor coexist in equilibrium state. The ideal gas temperature scale does not depend upon the nature of the thermodynamic or thermometric material. Okay, and the International Practical Temperature Scale was adopted by the International Committee of Weights and Measures, which are using based on number of easily reproducible fixed points together with the methods of interpolating with each other. And another one more important concept in temperature is, which would be useful in the second unit when you are moving to the next unit, the ratio of any two temperatures on the Kelvin or thermometric scale is equal to the ratio of the heat absorbed to the heat rejected by a Carnot cycle operating between the same temperature limits. Okay, and then now if we move to the recap corner for work and the heat energies. Heat and work or energy interactions which bring about change in the property of the system. Work is said to be done by a system if the sole effect on things external to the system can be reduced to the rising of a weight. Heat is a form of energy that is transformed across the boundaries by virtue of temperature difference. Heat is a form of energy, and work is also another form of energy. Work done by the system is taken as positive, and work done on the system, that is absorbed by the system, means then it is taken as negative. Heat flow into the system is taken as positive, and heat flow out of the system or from the system is taken as negative. The salient features of heat and work or energy, both or energy in transit, and can be identified only during the course of interaction or crossing the boundaries. They are boundary crossing phenomena. Their differential is not exact like other properties. They are so thus they are called inexact differential, and they are represented with the del q and del w, whereas other properties are expressed in terms of dp dt, that is exact differential. So t2 minus t1 could be found out, but q2 minus q1 cannot be found out. Instead, since they are inexact differential, it is meant that q1 to 2 only could be found out. What is this q1 to 2 is nothing but when the system moves from the state 1 to state 2, what is the net heat come in or goes out of the system? What is the heat transferred during the system change from one state to another state can be represented, and hence they are considered as a path function and not a property of a system. They could not be stored in the system. Heat like work can be stored by a system. Accordingly, it is wrong to say total heat or total work of the work content of the system. The unit of work is Newton meter or joule, and the rate of work in a work energy is called power, which is denoted as joules per second or kilojoules per second, so that we are describing it as kilowatt or watt, that is joules per second meant for watt. Apart from displacement work pdv, the other forms of work which are involved during the interactions or elastic work, stretching of a liquid film, shaft work, electrical work, polarization, magnetization, etc. The specific heat of the substance is defined as the amount of energy required in the form of heat of a change the a temperature of a unit mass of the substance by 1 degree. So C specific heat is equal to Q divided by M into dt, that is joules per kg Kelvin. For gases, two specific heats are quoted, namely specific heat at constant pressure Cp and specific the specific heat at constant volume is Cv. Okay, for air, the value for Cp is 1.005 kilojoules per kilogram Kelvin, and Cv is 0.718 kilojoules per kilogram Kelvin. Ratio of Cp by Cv is a symbol gamma, or called adiabatic exponent. For air, adiabatic exponent is 1.4, and the mass, volume and molar specific heats are correlated by the expressions by C is equal to C volume by capital M. M is molecular mass, whereas C volume is nothing but specific heat at standard thermodynamic conditions. Okay, so now here students, I have given the essence or important points or salient features which we have covered in the first unit. Now in this video I am not detailing anything, simply I explained you the important definitions and the key points for understanding the concepts only. Let me continue the same type of recap in the next video also, and then we will move to next unit. First, what you do is you just try to know the definitions, terminologies and basics, understand their types. Okay, and then try to do the simple problems so that you could able to check yourself whether you are how you are in theory part. After completing the theory part, please move on to the solving the problem, because without knowing the theory part it is not at all possible to get into the problems. Okay, so let me continue the same recap and key points in the next video. Thanks for patient listening. Let me continue in the next video. I am Dr. Suja, now signing off in this video. Meet you in the next video. Bye. happy learning. Keep on learning. Enrich your knowledge by exploring the things and watching the videos.